Hello, I'm Asmelier, and this is my physics final for Physics 270 with Dr. Koss. And for my first problem for Chapter 11, I have a question that reads: A student sits on a freely rotating stool holding two dumbbells, each of mass 3 kilograms. When his arms are extended horizontally, the dumbbells are 1 meter from the axis of rotation, and the student rotates with an angular speed of 0.75 radians a second. The moment of inertia of the student plus stool is 3 kilograms times meter squared and is assumed to be constant. The student pulls the dumbbells horizontally to a position of 0.3 meters from the rotation axis. And then part A asks, find the new angular speed of the student. And part B asks, find the kinetic energy of the rotating system before and after he pulls the dumbbells. So first, total angular momentum of a system is conserved when there is no external force or external torque acting on the system. Li is equal to Lf. So Li is initial angular momentum, and Lf is final angular momentum. Applying conservation of angular momentum, we get inertia initial times angular speed initial, and that equals inertia final and angular speed final. The expression for rotation kinetic energy is K is equal to 1/2 IW squared. And then doing calculation, we have our I total, which is inertia of student stool plus inertia of dumbbells, and then the moment of inertia for dumbbells is I dumbbells is equal to mass of dumbbell times r squared plus mass dumbbell plus r squared, and then that's going to be equal to 2 mass dumbbell times r squared. And r is the distance between axis of rotation to arm. Now we sub in the value. Now we sub in before. So now we're going to solve for the inertia before an arm pulls in. So we have our inertia is equal to inertia student stool plus our inertia of dumbbells. So plug in numbers for the values. So we have inertia is equal to 3 kilograms times meter squared plus 2 times 3 kilograms times 1 meter squared, and that gives us 9 kilograms meter squared. And then the moment of inertia of student stool and dumbbell systems after the student pulls inward. So inertia final is equal to inertia student stool plus 2mdr squared, sub in values, and we get 3.54 kilograms times meter squared. And now we're finding our W final. We have inertia initial over inertia final times our W initial, and we get 1.91 radians per second for W final. For B, kinetic energy of the system, we have Ki is equal to 1/2 inertia initial times W initial squared. Ki is equal to 1/2 times 9 kilograms times meter squared times 0.75 radians squared, and that gives us 2.53 joules. And then our kinetic energy final, we have 1/2 times IF times WF squared, and then our values are 6.46 joules for our kinetic energy final. And then for the second question, this is on chapter 12. We have a question that reads, figure P12.17 shows a claw hammer being used to pull a nail out of a horizontal board. The mass of hammer is 1 kilogram. A force of 150 newtons is exerted horizontally as shown, and the nail does not yet move relative to the board. Find A, the force exerted by the hammer claws on the nail, and B, the force exerted to the surface on the point of contact with hammerhead. Assume the force the hammer exerts on the nail is parallel to the nail. So two things for an equilibrium of an object. We need the net force. The net external force must be 0, and 2, the net external torque on the object about any axis must be 0 as well. So we have a little diagram. R is our reaction force, and N is our normal force. And then moving on to calculations. So first we apply the second condition for torque and taking a moment about point P in counterclockwise direction. So we have R cosine 30 times 5 centimeters minus 150 newtons times 30 centimeters. And then that's going to give us 1,039.2 newtons, or 1.04 kilonewtons. And then in order to keep the hammerhead in the correct spot, there's a frictional force in the positive x direction. Now we use the first condition. And then we get F minus R sine 30 minus 150 newtons. And our F is going to be equal to 370 newtons. And now, getting our directions, we solve for to get our I hat and J hat. We get now we're getting J hat. So we have N minus R cosine 30, and then N is equal to 1.04 times 10 to the 3 newtons times cosine 30, which is 901 newtons. And that is we have 370 newtons in the I hat direction plus 901 newtons in the J hat direction, finishing up this problem. And then for the third problem of chapter 13, we have a satellite of mass m, originally on the surface of Earth, is placed into Earth orbit as an altitude h. A, assuming a circular orbit, how long does the satellite take to complete one orbit? B, what's the satellite's speed? And C, what is the minimum energy input necessary to place this satellite in orbit? Ignore air resistance, but include the effect of the planet's daily rotation. Represent the mass and radius of the Earth as ME and RE, respectively. So we have gravitational force provides necessary centripetal force, which lets it revolve around the Earth within a certain period on time. So our centripetal force on the satellite is Fc is equal to mRw squared. And then our g-force on the satellite is Fg is equal to our gravitational constant times our mass of the satellite times our mass of the Earth over r squared. At equilibrium, we have Fc is equal to Fg. And then we solve for W. And when we solve for W, we get the square root of gravitational constant times our mass Earth over r cubed. Our angular speed can be expressed as 2 pi over t, and then when we replace W with 2 pi over t and solve for t, we get t is equal to 2 pi times the square root of r cubed over gm. Moving on to our calculations. The radius is the sum of the radius of Earth and altitude from surface h, so r is equal to capital R plus h. And then we input those values. T is equal to 2 pi times the square root of capital R plus h cubed over gm. And then the time period of the revolution made by a satellite is equal to 2 pi times the square root capital R plus h cubed over gm. And then B, our angular speed, can be expressed in terms of orbital speed v as follows. So W is equal to v over r. And when we replace W with v over r, we get v over r is equal to square root g times mu over r cubed. And then when we solve for v, we get v is equal to gm over r. Replace r with r plus h. And our orbital speed is equal to v is equal to square root g mu over r plus h. And then the minimum energy required is delta energy minimum is equal to negative 1/2 g mass of the Earth times mass of the satellite times 1 over R2 minus R1. R1 is equal to the radius from the Earth's start, and then R2 is equal to radius of the Earth plus our height. And then subbing in values, we get our energy minimum is equal to GM, mass of the Earth. So G, mass of the Earth, mass of the satellite over height over 2 times RE plus H. And that will be it for this chapter 13 question. And then for the last question on chapter 14, we have the following question. The spring of the pressure gauge shown in figure P14.7 has a force constant of 1250 Newton meters, and the piston has a diameter of 1.2 centimeters. As the gauge is lowered into the water in a lake, what change in depth causes the piston to move in 0.75 centimeters? So P is equal to our density times acceleration due to gravity times our depth. And then to start, we observe Hooke's law, which is F equals to minus kx for force needed to move the piston. And then inputting our values and solving, we get 9.38 newtons of force. And then P is equal to F over A, pressure needed to cause the force on that area. And now we're going to do the area of our piston. So A is equal to pi times D over 2 squared. And that's going to be equal to 0.000113 meters squared. And then solving for pressure, we get 82,900 pascals. And then we get P is equal to PGH, so we have 82,900 is equal to 1,000 kilograms times meters cubed times 9 meters per second squared times our H. And then solving for H, we get 8.46 meters. And then that is it for this final. Thank you so much. Have an awesome summer. Thank you so much.